Welcome to the deep dive. Today, we're getting into one of the most, well, profound ideas of the 20th century, right up there with relativity. I'm talking about quantum mechanics.
Absolutely. Its influence is huge. Think about GPS accuracy, the semiconductors, and,
Yes,
everything. Your phone, modern communication, it's really monumental.
it is. And quantum mechanics has been incredibly successful, hasn't it? Explaining things from the tiniest particles right up to, like, biomolecules.
Unprecedented success, yes. But, and this is a big but, there's this fundamental kind of unsettling question still lingering, the quantum measurement problem.
Okay, the measurement problem. Let's unpack that a bit. We use measurements, obviously, to see what's going on in the quantum world.
Right, that's our window in.
But the measurement itself, that's a physical process too, isn't it? So how does our normal classical equipment get a single definite result? When the quantum particles themselves are in these fuzzy superpositions or entangled in these, what did Einstein call them, ghost-like ways?
Exactly, that ghost-like connection. It feels like we're trying to pin down smoke.
Yeah. So how does that work? How do we get one answer?
And that's the core of it. It's a puzzle physicists, philosophers, too, have been wrestling with for, well, a century now.
So our mission today is to explore this whole discussion, look at how the ideas develop, the formalisms, the big philosophical questions it raises.
And the different interpretations people have come up with. We'll definitely be spending a good amount of time on decoherence, which is a potential explanation.
But ultimately, we'll leave it up to you, the listener, to decide if the problem is really, truly solved.
Sounds like a plan.
All right, so to get a handle on this, we need some key concepts. First, superposition and probability. Quantum mechanics basically says particle properties aren't always fixed, right?
Exactly. They're not always well defined. We can only predict the probabilities of different outcomes if we do an experiment, not a definite result beforehand.
It's like the particles in all possible states at once,
Hmm.
until you look.
Sort of, yes. That's the essence of superposition. And then there's entanglement.
Ah, yes, entanglement. This is where it gets really weird, doesn't it?
It certainly feels weird to our classical intuition. Particles can become linked, their wave functions become non-separable, their properties stay connected, interdependent, even across vast distances.
Einstein's spooky action at a distance.
That's the one. It sounds almost supernatural, but it's been proven experimentally over and over.
And it's not just a curiosity. It has real potential, like for unbreakable codes, quantum computing.
Huge potential, yes.
So let's illustrate this measurement problem more clearly. Imagine a simple system, S, maybe a particle that can be spin up or spin down.
Okay, a simple two-state system.
Now this system S interacts with our measurement device. Let's call it A. What happens then?
Well, the standard quantum mechanical description says the interaction leads to an entangled state. System S and apparatus A become linked. They end up in a superposition of all the possible outcomes.
So it's not just the particle is spin up or spin down. It's like the particle is spin up and the apparatus shows up is mixed with particle is spin down and the apparatus shows down.
Precisely. The whole combined system is in this mixed state. But we never see that. We only ever see one definite result, spin up or spin down.
And that's the problem. How do we get from that mixed up superposition to the single result we actually observe?
Right. To get that definite result, we need an additional assumption, usually called the reduction or the collapse of the wave function.
The collapse.
Yeah.
That feels like the central mystery here.
It is. How, when, why does this collapse happen? That's the grand question we're approaching. And there are related issues too, like the problem of the most suitable basis, why this specific outcome basis.
It really drives home the difference from classical physics, doesn't it? Classically, measuring something, like weighing that apple, barely affects it.
Mm-hmm. The influence is negligible.
But in quantum mechanics, the act of measuring is a significant interaction. It fundamentally affects these tiny energy states, thanks to Planck's constant.
It's not passive observation, it's active participation in a sense. Which brings us to the early interpretations. Niels Bohr and the Copenhagen view.
Right, Bohr. What was his take back in the, 1920s?
Bohr was, well, quite pragmatic about it. He essentially said, look, the measuring apparatus works classically. Observation causes the quantum wave function to reduce, and the apparatus shows just one value.
So he just drew a line. Quantum stuff over here, classical instruments over there.
Pretty much, a sharp dividing line. He wasn't looking for some perfect mathematical formula for it all. He felt that might miss the essence.
A practical approach maybe? Shut up and calculate, as some later put it.
That phrase captures some of the spirit, yes. But not everyone was satisfied with just accepting the collapse as a brute fact. Werner Heisenberg, for instance.
Heisenberg, yeah. He worked closely with Bohr, but had a slightly different angle.
He did. He talked about maybe an upper maximal size for quantum effects, a sort of Heisenberg limit. He thought of the wave function reduction more like a transition from potential to actual.
Potential to actual, like possibilities becoming reality.
Something like that. But the person who really put the mathematical framework in place was John von Neumann.
Von Neumann, 1932, a mathematician. What did he bring to the table?
Rigor. He introduced the formal concepts of operators and observables, the mathematical tools we use to connect quantum states to measurable quantities. They're like the bridge.
Okay, so he formalized the math. How did he handle the measurement process itself?
He described two fundamentally different ways a quantum state can change. Type 1. Discontinuous, non-deterministic, irreversible changes during measurement. That's the collapse.
Okay, the weird one.
And type 2. The continuous, deterministic, reversible evolution described by the Schrödinger equation when no measurement is happening.
So, two different processes. How did he connect them in a measurement?
He saw measurement as a two-step thing. First, the object and apparatus interact and become entangled. Their combined wave function evolves smoothly, deterministically, according to Schrödinger. All the quantum coherence, the phase relations, are still there.
Still in that mixed superposition state we talked about.
Exactly. Then comes step 2, the active observation. This is where von Neumann introduced his projection postulate, essentially formalizing the collapse. A macroscopic device somehow singles out one specific pointer state.
The pointer state.
Yeah.
Like the needle on the dial pointing to a specific number.
Precisely. And von Neumann seemed to suggest, maybe tentatively, that the ultimate source of this collapse might lie in the observer's consciousness.
Oh, consciousness. That really opens a philosophical can of worms, doesn't it?
It does. If consciousness itself is part of the physical world, maybe even describable by quantum mechanics eventually, where do you draw the line? It has echoes of, ancient ideas like Anaxagoras distinguishing mind from matter.
Mind separating things out. It's deep stuff. And the implications ripple outwards, right? This idea of superposition, if taken seriously everywhere, suggests a kind of holistic universe.
An indivisible world, yes, where everything that interacts becomes entangled. It resonates with ideas like Aristotle's the whole is more than the sum of its parts, very different from the old Newtonian clockwork universe.
And what about time? You mentioned the Schrödinger equation is time reversible, like classical laws.
That's right. The basic equations don't prefer one direction of time, but the collapse, the wave function reduction, that feels irreversible, like something really happens that can't be undone.
So it suggests a directionality, an arrow of time emerging from quantum measurement.
It hints at it, yes, which is fascinating. And it pushes us to ask that ontological question. What is actually real? Does nature wait for us, for our observation and the resulting collapse, to decide which state to be in?
Which, of course, brings us to the cat.
Ah, Schrödinger's cat. Couldn't avoid it.
The most famous thought experiment in physics, maybe. Schrödinger took this up to show how weird things get if you apply quantum rules to everyday objects, right?
Exactly. He wanted to highlight the seemingly absurd consequences. You've got this cat in a box, its fate linked to a quantum event. Until you open the box and look, the cat is supposedly in a superposition of, well, both dead and alive.
It's become this iconic symbol of quantum weirdness. Was he seriously suggesting gaps could be in such states?
No, it was definitely rhetorical, a reductio ad absurdum. He was trying to force physicists to confront the measurement problem head on. Einstein felt similarly, didn't he?
Right. Einstein wasn't comfortable with it either. He felt quantum mechanics was incomplete. It clashed with his idea of local realism.
Local realism, the intuitive idea that things have definite properties whether we measure them or not, and that influences can't travel faster than light. Entanglement seemed to violate that for him, hence spooky action at a distance.
And maybe part of the difficulty is just us. Our brains, they operate classically, right?
Overwhelmingly, yes. The signaling speeds in our brains are way too slow for complex quantum computation. While individual quantum processes might happen in biology, the brain as a whole thinks classically.
So we're trying to grasp fundamentally non-classical phenomena with classical hardware. It's bound to be a struggle.
Absolutely. Which leads us to the different ways people have tried to bridge this gap, the different interpretations.
Okay, let's run through the main contenders. We mentioned the Copenhagen interpretation already.
The oldest, arguably still the most popular among practicing physicists. It stresses complementarity, wave-particle duality, position-momentum uncertainty. You can know one, but not both precisely at the same time.
And it accepts the collapse.
It accepts it, yes, but doesn't really explain the mechanism. It says observation causes it, and that's sort of that. Pragmatic, as we said.
Then there's the really wild one. Many worlds. Hugh Everett's idea.
Many worlds. Everett basically said, what if the collapse never actually happens? What if the wave function always evolves according to Schrödinger?
So, how do we get a single result then?
Everett's answer was radical. He suggested that every time a measurement could yield multiple outcomes, the universe splits. All outcomes happen, just in different parallel universes or branches.
So in one universe, the cat lives, and in another, it dies.
Exactly. We only experience one branch, so it looks like a collapse happened. It's incredibly ambitious, maybe elegant in a way, but while most physicists treat it more like a fascinating thought experiment, it's hard to test.
Right. No messages from the other universes yet. What about trying to make it deterministic again? Pilot waves.
Pilot wave theory, or Bohmian mechanics. Started by de Broglie, developed by David Bohm, the idea is to add hidden variables, extra information we don't see that determine the particle's actual path. A pilot wave guides the particle.
So it gives definite results. Avoids the probability issue.
It does give definite result and trajectories, yes, but the cost is high. You need to know these hidden variables precisely from the start, which seems impossible, and it generally requires faster-than-light influences, which conflicts with relativity.
Okay, so that has its own problems. What about theories that say the collapse is a real physical process, just one we don't understand yet?
Those are the explicit collapse theories, like GRW theory, Girardi, Rimini, Weber. They propose that the Schrödinger equation isn't perfectly correct. There are tiny, random, nonlinear hits or perturbations that spontaneously cause wave functions to collapse.
So it just happens sometimes, more often for big things.
Exactly. The probability of collapse is tiny for a single particle, but becomes almost certain very quickly for macroscopic objects made of many particles. It solves the problem, in a sense, but it feels a bit ad hoc. There's no deep physical reason proposed for why these collapses happen, although some link it to gravity, and no experimental proof so far.
Feels like adding an extra rule just to fix the problem.
That's the main criticism, yes. And briefly, there's also consistent histories.
Consistent histories.
Developed by Omnes, Griffiths, and others. It tries to describe sequences of quantum events or histories in a logically consistent way without invoking collapse during the process. It focuses on probabilities of entire sequences.
Avoiding collapse again.
Yes, but it implies a kind of infinite chain of conditions across the universe to define a consistent history. Its applicability has been debated.
Okay, that's a lot of different ways to think about it. But now let's focus on decoherence. You said it's maybe not just another interpretation, but an attempt at an explanation.
That's the key distinction, yes. Decoherence isn't necessarily a full interpretation on its own, but it uses standard quantum mechanics to explain why quantum systems start to look classical when they interact with their environment. It tries to bridge that gap.
How does it redefine the quantum versus classical difference?
It focuses on entanglement and phase relations. Quantum systems can be entangled. Their wave functions have definite phase relationships between different parts of the superposition. Classical systems don't have this. Decoherence is the process by which interaction with the environment effectively washes out or smears out these delicate quantum phase relations.
So the environment is key. It messes up the quantum coherence.
Precisely. And we used to think entanglement was rare, exotic.
Right, you mentioned that. But now we know it's everywhere.
Well, it's potentially happening constantly all around us whenever systems interact. It's just that the effects usually vanish incredibly quickly because of decoherence.
Which brings us to this decoherence time, Taka. How fast are we talking?
We're talking fast. Taka is the timescale over which these quantum phase relations survive. It depends on the system and its environment, but for macroscopic objects, it's often unimaginably short. After TOG, the system effectively looks like a classical statistical mixture. You can't tell it apart from something that just had probabilities from the start.
So this explains why we don't see quantum effects in everyday life. Because systems are constantly interacting with their surroundings. Open systems, not the closed systems in textbooks.
Exactly. Most real systems are open systems. Think about that ammonia molecule example.
The NH3 molecule, right? Nitrogen tunneling back and forth.
In a vacuum, it's in a nice quantum superposition. But put it in air, even at moderate pressure, and collisions with air molecules happen constantly. These collisions act as environmental interactions.
And they cause decoherence.
They do. They effectively measure the nitrogen's position, destroying the superposition. The decoherence time is estimated to be around 10 to the minus 10 seconds in air at half an atmosphere. Tiny fraction of a second.
Wow. Okay, so the environment is constantly measuring things in a way.
In a sense, yes. It leads to this distinction between weak and strong measurements, too. Weak measurements might only create partial entanglement, extracting limited info, like in the Stern-Gerlach experiment.
But strong measurements.
Strong measurements involve more thorough interaction, maybe with the measuring device and its surroundings, leading to essentially complete decoherence in what looks like a full wavefunction collapse.
You mentioned tables from Jews and Zay showing decoherence times. How fast can it get for bigger things?
Mind-bogglingly fast. For something like a tiny dust particle, just a micrometer across, interacting with air molecules, the decoherence time is estimated at around 10 to the minus 36 seconds.
Minus 36. That's instantaneous for all practical purposes.
Utterly instantaneous. A large molecule in air, maybe 10 to the minus 30 seconds. These times are often many, many orders of magnitude faster than the time it takes for the object to even reach thermal equilibrium with its surroundings.
So the implication is there's no fixed size limit, no Heisenberg limit where quantum mechanics stops working.
Exactly. It's not about size, it's about interaction and isolation. The time scale of observation matters. If you could somehow take an extreme snapshot, faster than the decoherence time, everything would look quantum mechanical.
Our world looks classical because decoherence happens too fast for us to perceive the underlying quantum nature.
That's the core idea of the decoherence explanation.
But we can see quantum effects in larger systems sometimes, right, if we protect them.
Yes. If you can isolate systems very, very well from their environment, like those entangled ions trapped in an ultra-high vacuum, they can maintain coherence for maybe 1/100th of a second. Or experiments showing interference with big C60 buckyball molecules over milliseconds.
And things like superconductors, LIGO mirrors.
Those exploit macroscopic quantum coherence. It can be done, but it requires extreme isolation or special conditions.
So going back to consciousness, if decoherence happens this fast, especially for anything interacting with an environment,
then the idea that human consciousness causes the collapse seems highly unlikely. Neuron firing times are around 10 to the minus 2 seconds, vastly longer than typical decoherence times for anything complex interacting with an environment like the brain. The collapse, or rather the appearance of collapse due to decoherence, must happen long before any signal reaches our conscious awareness.
the environment does the job way before we're involved.
That's the perspective decoherence offers. Wojciech Zurek has been hugely influential here. He talks about the system S interacting with environment E1, which interacts with E2, and so on, a whole chain.
Okay.
And while for a perfectly isolated system plus environment, the quantum information might theoretically reappear later these Poincare recurrences, the timescale for that to happen grows astronomically with the number of particles involved. For any realistic macroscopic system, it's effectively permanent.
So the information isn't truly lost, it's just hidden, spread out.
Exactly. In the decoherence picture, the total wave function of the system plus the entire environment never actually collapses in the old sense. The quantum coherence, the phase information, just gets diluted, effectively lost into the correlations with the countless degrees of freedom of the environment. It's hidden, not destroyed.
Like that drop of ink spreading out in the ocean.
A good analogy. And Zurek introduced concepts like pointer states. These are the robust, stable states of the apparatus that the environment preferentially selects.
The ones that survive the environmental interaction.
Right. An environment-induced superselection or inselection, the environment acts like a constant monitoring system, selecting these stable pointer states and ensuring we get consistent, classical-like measurement results.
Okay, so decoherence offers a mechanism rooted in standard quantum mechanics for why the quantum world looks classical to us. It points the finger at the environment.
It provides a quantitative physical explanation for the transition, yes.
So, where does that leave us? Is the measurement problem solved?
Well, there's been huge progress, especially since the 80s, understanding these open quantum systems. From a practical point of view, many physicists consider decoherence a FAPP solution.
FAPP.
For all practical purposes. It explains why we observe what we observe using the existing quantum framework. It lets us calculate things and make predictions that work. It saves orthodox quantum mechanics without needing fundamentally new physics or weird interpretations, arguably.
There are still objections, right? You said the information isn't really lost, just hidden.
That's the philosophical sticking point for some. If the total wave function never really collapses, if all the possibilities are still there in the correlations with the environment, Have we truly solved the fundamental problem of why we experience only one reality? Have we just moved the problem into the environment?
So it explains the appearance of collapse, but maybe not the ultimate nature of reality itself.
Perhaps. Or maybe, as some argue now, the very idea of collapse was the wrong way to frame the question in the first place. It was a concept the pioneers introduced to make sense of their results.
And now,
Now, especially in fields like quantum computing and quantum information, physicists often work hard to avoid collapse and decoherence, only performing a measurement right at the end to read out the result. The focus shifts. Maybe collapse isn't a fundamental process, but just what happens when quantum information inevitably leaks into the wider world.
so a change in perspective might make the problem feel less like a problem.
It might. It still marks that crucial boundary between the quantum and classical realms, but maybe it's less of a paradox and more of a physical process we now understand much better thanks to decoherence.
Well, this deep dive has certainly taken us through some mind-bending territory, from the early struggles with superposition and measurement,
Through Bohr, von Neumann, Schrödinger's cat, all the different interpretations.
to the really powerful insights decoherence provides about the role of the environment. It's been quite a journey through a century of thought.
It really has. And it leaves us, and you, the listener, with a final thought to chew on.
Go for it.
If decoherence is right and quantum information is never truly lost, just diluted and hidden in the environment, does that imply our solid, everyday classical reality is, in a way, just a persistent illusion, a kind of projection selected and maintained by the universe, constantly observing itself? Is the definite world we experience just the tip of the iceberg emerging from a vast, hidden quantum ocean?
A grand illusion continuously monitored into existence. That's definitely something to ponder. We hope you'll continue to explore these deep questions about reality, observation, and the strange, fascinating world of quantum mechanics.